Welcome everyone to this new lesson in remote sensing techniques. In this lesson we will concentrate on the questions how to analyze a digital elevation model, and especially how to analyze DEMs derived by the shuttle radar topography machine, also called SRTM, and with some kind of pixel size of about 90 meters. And first of all, we will change the system today, because this is not, as you can see, this is not as imagined. It is the ArcMAP Arc info from S3 interface you can see here in the version 10. And for this lesson you will need some digital elevation model you can get from the Global Land Cover Facility, also known by the URL landcover.org. By going there you will need to use the SD interface or ESD interface. Please check out my other videos how to get some data from this GUI. First of all, let me explain you some things about ArcMAP. So you have the layout or the data view here, where you can see the raster. Then you have some kind of list of layers. You will have a result here maybe when you're starting it, and maybe the most important one is the Arc toolbox you can use. And let us start with the just a new project. So this is a new project, and we will add some data here. This is more or less now the dialog where to choose your data, and this is the original data. This is a processing limit level filled finished B, I think. And as you can see here, just by creating this new raster or adding this raster to the view, you will see some grayish picture, a blackish surrounding, and by using the identify button you can check the values. You maybe know that as inquire cursor in Atlas Imagine. As you can see, the outer space here is minus 32,768, which is the lowest possible number in the assigned 16-bit format. And there are also some original values, so elevation values in meters above sea level. As you can see here, regarding the ellipsoid WGS 84, you will have some heights about 1,300 for 2,000 meters, and in the upper left there are some higher peaks up to 3,000, 4,000 meters, and there are some lower areas here. But yeah, as you can see, this image doesn't show anything, which is quite useful. So we will, first of all, we will search for a function which is called, oh no, we don't search for it, it takes too long. So you will have this toolbox, and there are a lot of things to use, and especially the data management tools. By looking into the raster and the raster properties, you can recreate or recalculate the statistics of the layers, because the statistics in this image is a little bit distorted because of the highest and lowest values, and we will recalculate the statistics by double-clicking on it, choosing the raster dataset we would like to calculate. Ignore values is here minus 32,768. We will add this value to the list. Click OK. The old raster is created, and as you can see here, the results are calculated. And there we go. I'll put raster dataset. We'll add this to the image. I'm removing that, and you can see much more of the image. So you have the lowest values here, minus 26,000, which are probably here in the area here somewhere. Let's check out. Identify. Yeah, no, not really. So normally they should be there somewhere. So, but yeah, we are now having some kind of first impression of the digital elevation data, or the elevation data in our area of interest. And this is for the first hand. So you can also arrange the color ramp here. So just by using this, maybe invert to have the brownish things in the higher areas and the greenish color in the lower areas. But you can also check the properties, and therefore this is quite important to see here. So you have the color ramp. You can check by using minimum maximum to get a really good value, but this was not so successful. So let's go back to the histogram specification. No. Standard deviation, which provides best information here, and we can also use this value we have just ignored. We can use this value as the background color, and by using this we only have our area of interest where we have good values. So this is the first step. So now we have a digital elevation model. Everything is clear. So we are having some kind of low and high values, and you can identify each value by using the identifier button. Once again, so there are several derivatives maybe on that kind of data, because this is a topography. You can calculate the slope on every point, which is similar to the gradient, so the steepest slope of any slopes in any directions. And how to do that? Well, it's quite easy to do so. Just go on the spatial analyst tools. Maybe you can also use 3D analyst tools, spatial analyst tools, and therefore the surface. And you can see the possible functions here, and there's the slope function. So we have an input raster, which is probably more or less this SRTM value. You can also use a drop-down menu, and we will create a new raster dataset, which is called output raster in our folder. So there we are, and this is more or less slope in degrees.tif. There we go. We will use degrees instead of percent rise, and we don't have to change the Z factor. Let's go straight forward. Sometimes you will see directly the output. I've disabled this function, and I have to edit this for my own. So as you can see here, they have the green areas with nearly no slopes, with slope values, or really small slopes, small scales, I don't know, low values in slope. And you also have areas where you have higher values in slope, especially in the upper northwestern part. But one important thing to know is just look on this area here. Maybe you can see there's some striping in the image. And this is due to the sensor, so you can arrange this by making some kind of neighborhood analysis or a focal mean analysis on that, and recalculate this digital elevation model. Otherwise, just be prepared to see some features like that, like this striping in the digital elevation model. And if you were not able to use that function because of some kind of extension problem, you can also go to customize extensions, and you just have to check these buttons to activate. So this is the slope model. Everything looks fine so far, and we'll now go ahead. As you can see here, very high areas or high areas here, more or less really steep. And what we will do now is we will calculate a hill shade. What is that? So it's creating a shaded relief from a surface raster by considering the illumination, source angle, and shadows. You can also use a tool help to get some idea about the function and how does it work, and also the Python scripts that could be used to create the same result. So therefore we also need an input raster, and be prepared not to use the slope or something like that. So we will all concentrate on the SRTM values, and we also have to change the folders. So this is the aspect. No, it's a hill shade. .tif. And we will leave the azimuth and the altitude as it is. And we will maybe calculate the shadows to get a more plastical view on it, or to get a better idea about the topography. So as you can see here, that's this area. This is all brownish. So you don't have any differentiation between the higher parts and the lower parts, because it's all the same color. So the main or the best part on this hillshade is that you will get an idea about the aspect, or about the topography and where are the ridge lines. So by using this, you will have some values of about 0, which are probably directing southeast, I think, and in an angle of steeper than 45 degrees. And you also have here these values of 254, which are more or less inclined in the angle of 45 degrees and looking into northwestern directions. So by adjusting the display button here and also the transparency to 50% maybe, and by unchecking this one, you will get a very good idea about the topography in your area. So you can see the colors of the height, but also the hill shading which is laying above. So you will get a really good view on the topographic features. So this is hillshade, and we have created a slope value, and maybe you don't want to use these kind of classes here in the slope in degrees. You can also change that by using these layer properties and checking stretched instead of classified. You just have to arrange the color chart here, so we will go from green to red, which is quite nice. So, and we have to invert it because we are expecting green areas with no slopes, or with less inclined slopes. And as you can see here, you have the lower values of 0 and 89%. 89% is really rare, so it normally occurs here on the edge, because you will have this missing values, and therefore you will get these hardcore slopes, I will call them now. And here we have these highest values. You can also check all layers, identify it once more, and as you can see here, you have these the middle cell is 1157, but the corresponding other sides are minus 32,000. So that is the problem why it's doing that bad calculation on the edges. So this is now slope. We have hillshade. What is left? So we need an aspect. Where is the slope looking to? Therefore, we will also need the input raster, as I said, which is the SRTM data, and we will create a new layer which is called aspect.tif. Go ahead, straightforward. No difficulties in doing that. It's quite fast. Add this to the display, and this is now a little bit more. Well, I think it looks like some kind of psychedelic feature here, but let me explain it to you. You will have the aspect is telling you where the slope is heading to. So in red you can see the northern exposed slopes, which are looking into northern directions, and then you have the area of 22.5 degrees up to 67.5 degrees. These are the slopes looking into northeastern direction, and so far. So you have a pre-classified image in ArcGIS, which is telling you where the slope is looking to. Why is that important? Because some kind of hydraulic features are corresponding to them. So let's assume that you are having only northern, only difference between northern and southern exposed slopes, and of course the southern exposed slopes will dry much faster after a rain event than the northern exposed slopes. You will have these differences here. So, and you can see also a second possibility. So you have the lake area here, and they are connected to the value of -1 because they are flat areas, so they don't have any aspect. So this aspect, we have the hillshade, we have the slope. What is left? It's a second derivative. So the first derivative, which is also called the slope, will say to you, okay, how fast is the movement of maybe a hill slide or a rock fall. So you can calculate that by maybe rethinking about the pressure on the ground. But yeah, let me explain it like how fast is a movement on a given slope. So if it's steeper, it's faster. So what we are now looking is a second derivative, which is also called the curvature. And for the curvature, you also need the SRTM value. You will create a curvature raster, which is the overall curvature. I will explain it later. So it's a curvature.tiv. And z factor, okay, we are normally using meters, and therefore we don't need any z factorization. But there are two different output curvature rasters here you can create. So the first one is a profile curvature. So how is a movement? Is it accelerating, or is it braking, or decelerating? So if it's a convex profile curvature, you will have accelerating movement. If it's a concave curvature, you will have decelerating or braking of mass movement. So this is profile curvature. Look at your nose, look at the profile of your nose, and you will have some kind of feeling what is convex and concave. So then you have the output plane curvature raster, which is in another direction. So this is the let me just copy that. It's a plane curvature. The plane curvature is giving you an idea about the convergence or divergence of the mass movement. So if you have a convex slope, you will have divergent movement of any of sediment fluxes or fluxes as well. And if you have a convergent plane curvature, if it's a concave forms are divergent, convex forms are convergent. So the mass movement is concentrating on an area. So these are two different curvature files you will create here. You will just click OK. Look again to the results. They're created here, and we will now have a look here on the profile curvature. We'll add this to the display, and as you can see, the values are too far away, so we will create minimum maximum stretch, and we will edit the highest value to 1 and the lowest value to -1. So, and now you can see where we will have convex and concave forms. Let's have a look into the help function. Help file will tell you, okay, a value of 0 is indicating a flat surface, which is quite what we have accepted, but a negative value indicates that the surface is upwardly convex at that cell. That means that the mass movement is accelerating and maybe converging. And opposing that, if this value is positive, you will have a concave form at this cell. So let's go back into that. So you can just create these kind of profile raster files, and that's for the moment, I think. If you would like to make a map out of it, just go straight forward, check out my other videos where you can see how to make maps with ArcMAP. Thank you for watching. Goodbye.